Hello everyone. For this tutorial video, I'd like to explain how to figure out power series representation of specific functions, which will actually be important in the next tutorial video too. In particular, we remember the formula for a geometric series. Whether n is infinite or finite, is the coefficient a over 1 minus the ratio you are raising to the power of n, with the catch being the absolute value of r must be less than 1. This means if we have the infinite series of the function x to the power of n, we can see it is a geometric series, where the coefficient must be 1, and the ratio is substituted with x, and we use the same caveat, so absolute value of x must be less than 1. With some foresight, we can conclude that we can represent the function of 1 over 1 minus x as an infinite series of x to the power of n, provided the absolute value of x is less than 1. This fact helps us work with more complex functions such as this. We would rewrite this function as minus negative x cubed, so that we can condense it into a geometric series, as the geometric series formula involves a minus, where the coefficient a is 1 and where the r or ratio is negative x cubed, provided that the absolute value of negative x cubed is less than 1. Although this is technically correct, we should simplify it into a limit we can test more easily, so we factor out a negative 1 to the power of n, and see that the 3 and n multiply because of how exponents raised to exponents work. This is all provided the absolute value of x and then that absolute value cubed is less than 1, or upon simplifying, the absolute value of x is less than 1. Before we move on to Taylor and Maclaurin series, we should first take a quick pit stop at the derivative and integral of power series. We start our computation by noticing we can expand the part raised to the power of n, like so, and then for the derivative, we simply take the derivative of each term, which condenses nicely to the infinite series of n times the coefficient of n times x minus a raised to the power of n minus 1 rather than simply n. So, it is simply the power rule of derivatives, just in a format we are not typically used to. To get higher order derivatives, we would simply differentiate again and again, like so. And we would see we would get n times n minus 1 times coefficient of n times x minus a raised to the power of n minus 2 for the second derivative. And then we multiply this by n minus 2 and subtract 1 from the exponent to get the derivative of that, or the third derivative, and so on. We next compute the integral by saying the integral of the infinite series can be swapped around as the infinite series of the integral with respect to change in x. We do the inverse power rule for antiderivatives, so raise x minus a to the power of n plus 1 and divide by n plus 1. But we see, unfortunately, we get a second constant of integration that is not found directly from the antiderivative, and this comes from the infinite series. The derivative and integral may seem like useless trivia at first, but it is actually a vital tool in the Taylor and Maclaurin series, which is what we will investigate in the next tutorial video, and how you can use these series to represent a function exactly. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.